Well, hello again. In this example, you will learn how to perform moment distribution on a frame which has loads at the joints and as such experiences sway. We will look at this simple portal frame which has a 30 kip load being applied here. And just to confirm, you get a display shape that looks something like this, and there is going to be some kind of a displacement that occurs up here. And so this frame does indeed have sway. Modulus of elasticity for all members, 3600 KSI. I is constant for all of these members at 2400 inches to the fourth. So to handle these frames with sway, first thing we've got to do is we've got to lock against sway. So you notice how we had motion side to side, so I put a roller which would prevent that motion. And then I am simply going to take that roller and I'm going to pull it or move it a unit displacement right up here. And we will let that display shape come out as such. And what's going to happen is a reaction is going to develop here. A certain amount of force was required to pull that over. You also notice that that point load that we had on there initially is not currently present. What we are really looking for is we're looking for what is this reaction, or what is the force that is required to create a unit displacement. So in this case we're going to be working in units of inches, and so we will say what is it required to displace that 1 inch. Now we are using moment distribution, which means we need the distribution factors. So we will lock all joints against rotation, and since all members are the same length and they are all fixed, this can be done very rapidly. So the stiffness of BA is equal to the stiffness of BC, which happens to be equal to the stiffness of CB, which is equal to the stiffness of CD, which is 4EI over the length, which I will take as 1/5. We can get the distribution factors fairly quickly here. Distribution factor for joint B, for member BA, is the stiffness factor for BA divided by the total stiffness for that entire joint, which is equal to 0.5. And the distribution factor for BC is equal to 1 minus the distribution factor of BA, which is equal to 0.5. And in a like fashion, we could conclude that these other distribution factors are also equal to 0.5. Now we need to find the fixed end moments due to that sway. So I want you to notice that we've got a displacement here of 1.0 inches. This would be 240 inches in length. And so what we want to do is we want to look at a beam chart, and on a beam chart we have a member that is fixed, subjected to a displacement, so we'll just go ahead and plug that in as 1 inch. And then the moments are found as this 6EI delta over L squared, so let's get that written down. 6EI, 2400 inches to the fourth, over L squared, 240 inches, and that will be equal to 900 kip inches. So I now know what the fixed end moments are here and here. With that in hand, I am then prepared to put together my moment distribution table. A couple of things I want you to be aware of. This has completely run the example, but there are the fixed end moments that happen in those columns. And since joints B and C were fixed against rotation, there were no moments that developed here. Here's the distribution factors that we have going on, and then we will use the moment distribution method to balance the joint and then do carryover to each of those. And we are balancing all joints simultaneously in this particular example. And it continues on and on, until we find what the internal moments are at each of the joints. Let's go ahead and take these moments that we've got here in our columns, and let's translate those over to a free body diagram. I want to remind you one more time that the positive sign convention for moment distribution is that a clockwise moment is positive. So with that being a negative, it comes over here, and we can place this on here, 720.7, 539.6. And this actually is the same for both because it's a nice symmetric structure. And then we will complete out the free body diagram by sketching in my unknown shears. What I've done is I've sketched the shears on there in their positive direction. If a shear causes a clockwise rotation, it is considered to be positive. I will then some moments about point B, and that will tell me what the shear of A is, and that actually computes out to be 5.25 kips. So I'll write that in. 5.25 kips, sum of forces in the x direction, tells me that V of B is 5.25 kips, and in a like fashion, 5.25 kips, 5.25 kips. Now that I have done that, I can come back here, and this is the response for that unit displacement. I know what the shears are, 5.25 kips, 5.25 kips, and remember we had this roller up here which had a reaction summing forces in the x direction. I know that that is 10.5 kips. So what this really is telling me is that if I apply 10.5 kips to my frame, it will displace 1 inch. You will recall that what is actually being applied to the frame is 30 kips. So we're going to get a scale factor, which is my actual load divided by the force that would develop if we had a unit displacement, and that is 2.857. So remember, I have the responses right here due to that 10.5 kips. So if I want to know what it is for 30 kips, I will take these quantities and I will scale them up according to the scale factor. So, for example, the moment at A is equal to the moment at D is equal to that 720.7 kip inches, and scale it up by this factor 2.857, and that is equal to 2059 kip inches. And the internal moment at B is equal to the internal moment at C, and that's 539.6 kip inches, multiplied by that scale factor 2.857, and that will give me an internal moment of 1,541.6 kip inches. Now, one other little piece of information that you may be interested in is we knew that when we applied 10.5 kips that the displacement was 1 inch. So if I want to know what it is when I apply 30 kips, multiply that by the scale factor, and that'll tell me that the displacement is 2.857 inches. That concludes this example. As always, it's a beautiful day for studying structures.